Our next unit to discuss is that of the planets of our solar system. I've entitled this unit The Wanderers because astronomers hundreds of years ago didn't really know what the planets were except for the fact that they seemed to wander across the sky with respect to the stars. In other words, they did not always follow the same pattern that the stars followed. We're going to do this study in several parts. The first part today will cover the origin of the solar system and its structure, as well as a look at the planet Mercury. So what does our solar system consist of? Mostly, to tell you the truth, the solar system consists of the sun. By mass, that is, almost all of the mass of the solar system is concentrated in the sun. If you added up the mass of all of the planets, asteroids, comets, etc., dwarf planets in the solar system, you would come up with less than 1/700th of the mass of the solar system. So that means we make up much less than 1% of the solar system. And that's with all the planets' mass added together. So similarly to our very first lecture, this should make us feel relatively insignificant compared to the vast mass of the sun. But the sun does have these things that are orbiting it, small as we may be. The inner planets in our solar system are the rocky worlds, which we call the terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, and Mars. That's in order from closest to the sun to farthest from the sun. The outer planets are gaseous and large. They are Jupiter, Saturn, Uranus, and Neptune. There is an asteroid belt in between Mars and Jupiter, which separates the terrestrial planets from the gas giant planets. In addition, there are dwarf planets which orbit the sun at various distances. Some are as close to the sun as the asteroid belt, and others are farther away from the sun beyond the orbit of Neptune. Speaking of beyond the orbit of Neptune, outside of Neptune's orbit lies a region called the Kuiper Belt. Neptune is somewhat close to this region, and so there are objects which in their orbit maybe spend most of their time outside of Neptune's orbit, but during some points in time come inside to where Neptune would be orbiting. Now they don't collide in this process because Neptune is generally somewhere else in its orbit when those objects reach a nearer point in their orbit than where Neptune orbits. Pluto is an example of such an object, as is Eris, and these are called trans-Neptunian objects because they transit between the outside and the inside of Neptune's orbit. The Kuiper Belt consists of many such objects. Some are even larger than Pluto. This should start to get into the idea of Pluto as a dwarf planet, I hope. Because were we to maintain Pluto's status in name as a planet, then by all rights we would need to call all of those countless objects in the Kuiper Belt that are at least as large as Pluto planets also. And suddenly, population of planets in our solar system will go from 9 to many, many more that we couldn't possibly keep track of. But there are better reasons for Pluto's reclassification, which we will talk about next. Incidentally, notice that on the picture on the right, the terrestrial planets are make up these tiny little circles, well, near circles, in the inner part of the solar system. If we zoom out to 80 AU, in other words, you cannot even distinguish the difference between Earth, Venus, and Mars's orbit from each other. Only when we zoom in can we see that difference, even though it is across vast regions of space. So getting into the topic of Pluto's reclassification, you have to understand a little bit about the history of Pluto to understand its whole entire saga. The existence of Pluto was predicted to occur based on some anomalies in the other planets' orbits. However, when Pluto was discovered and eventually its size became clear, it was obvious that Pluto's tiny size could never possibly account for those anomalies because its gravitational influence would not be nearly enough. Indeed, those anomalies were probably just measurement error. However, Pluto was discovered in 1920 when searching for more worlds beyond Neptune. It was assumed that anything orbiting the planet in a regular way, anything orbiting the Sun in a regular way, would have been a planet. But as more and more became known about Pluto, it became clearer and clearer that Pluto wasn't really like the other planets. First of all, it's not very massive. What we mean by that is that for an object to really be considered a planet, it needs to have had enough gravity to clear the neighborhood of its orbit of objects of comparable mass. In other words, those objects would have collided or been bounced out of that orbit through the strength of the gravity of a large enough object. Pluto, being a Kuiper Belt object, amongst many others similar to its size and shape, has done nothing of the sort. In fact, 7 moons in the solar system are actually larger than the dwarf planet Pluto. And also, it's worth noting that while most of the orbits of the planets in our solar system are nearly circular in appearance, Pluto's orbit takes on a much more elliptical path. Its orbit is also inclined with respect to the plane that most of the planets orbit on, making it a very different orbit indeed. Let's look back at this picture once more. Notice how offset the orbit of Pluto is compared to the other planets in the solar system. Just like other objects in the Kuiper Belt, Pluto transits between the inside of Neptune's orbit and the outside of Neptune's orbit. In other words, it is sometimes closer to the Sun than is Neptune. This tendency is very typical of objects in the Kuiper Belt. My personal gripe is that back in the 1980s, when I was a child, learning the order of the planets, it was burned into my brain that the planets went in order from the Sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Well, it just so happened that during the 1980s, that was not even true. At that point in time, Pluto was inside of Neptune's orbit, making it closer to the Sun than Neptune. This lack of clarity of actually where Pluto orbits is just indicative of the highly elliptical nature of its orbit compared to the other planets. But ellipticity of how elliptical an orbit is on its own is not enough of a reason. All of these other attributes of Pluto point towards it being a very different object than genuine planets of the solar system. Therefore, in 2006, after most astronomers had already accepted that Pluto was really not a planet in the true sense of the word, the new term was coined dwarf planet. Pluto is but one of several, many actually, dwarf planets in our solar system. Okay, but let's go beyond the orbit of the Kuiper Belt. Kuiper Belt extends out to 50 AU. That means 50 times the distance from the Earth to the Sun. Well beyond that is the region known as the Oort cloud, which extends out to at least 100,000 AU. This is an enormous cloud, almost spherical in shape, which is comprised of cometary bodies. These comets, if knocked by the gravity of, say, an approaching star or a passing star, can get knocked into an orbit which causes them to plummet towards the Sun in a very elongated path depicted here where it says typical comet orbit. Until it gets knocked into such a way, it doesn't really become a comet that we think of with a tail. It's just a cometary body that is very slowly orbiting the Sun way out in the region of the Oort cloud. But once it takes on a typical comet orbit, it plummets in towards the Sun, growing a tail from the heat of the Sun, burning off the ice from the object. There are many similarities, even though there are many differences, in the objects of our solar system. For example, all the planets orbit in the same direction, and they are more or less on the same orbital plane. Again, Pluto, being the oddball dwarf planet, not the only oddball dwarf planet, but previously called a planet, exhibits more of a tilt than the other objects, the true planets in our solar system. We see it depicted here at a 17-degree angle with respect to the plane of the solar system. Mercury is tipped by a bit more than the others as well, but still not even half that of Pluto. In addition, most of the planets rotate on their axes in the same direction. Venus is the exception. It rotates the opposite direction, as does the Earth and the other planets. And Uranus is a bit odd too, because it's almost tipped on its side as though it's lying down. So its rotational axis causes it to rotate almost perpendicular to the axis of the rest of the planets. Now, you're not going to be held responsible for these equations here, but we can determine something about the density of a planet even without actually visiting it or being able to weigh it directly. We can do this, first of all, by using Kepler's third law to determine the mass of the planet. Notice that this is called Newton's modified form of Kepler's third law. Kepler only knew the proportions of orbital distance to period. Newton was able to specify through the force of gravity, his understanding of the force of gravity, the exact numbers to calculate the mass and exact orbit of a planet. In any case, using this equation, we can find the mass of a planet based on its distance to the Sun and its orbital period. Once we know that mass, we take our understanding of the distance again, and instead of using it to calculate the mass, we can use the distance in combination with the angular size that we see to figure out what the radius of the planet is. and knowing its radius allows us to calculate the planet's volume. Thus, having calculated the planet's mass and the planet's volume, we can determine the planet's average density by simply dividing the mass by the volume. This may not seem significant, but average density actually tells us a lot about a planet. Because we know that the inner planets have a high average density, then we can say something about their composition. Clearly, if the planets were composed mainly of gas, we could not have such a high average density. Thus we know that the terrestrial worlds are mainly rock and maybe metals like iron or nickel. On the other hand, low-density planets, like the outer gas giant planets, imply that for such a low density we must have some kind of substance, like gas or ice, to account for the composition of the planet. Saturn's density is so low, in fact, that if you could have an immense ocean to float Saturn in, it would just float on top. It is less dense than water, in other words. The next unit is a review of the origin of the solar system, which we've already discussed when we talked about the history of the Earth, so I'm going to go through this relatively quickly. We talked about dating, figuring out the date of how old the solar system is. Radioactive dating is a reliable way to do this, and even though it has errors, these errors are only on the order of thousands or maybe millions of degrees, but definitely not billions of degrees. I'm sorry, years, not degrees. And the oldest samples that we have been able to find from meteorites and on Earth points towards an origin time of about 4.5 billion years ago. The most plausible theory to explain how the solar system came to be is that of the solar nebula theory. This theory suggests that a large cloud of gas and dust eventually began spinning and shrinking as gravity attracted the particles in it to each other. As it shrunk, it spun faster and faster because of the law of conservation of angular momentum. Eventually, this process caused the sun to form in the center, and the remaining gas and dust left orbiting the central sun was what the planets formed out of. The material in that cloud of gas and dust eventually condensed, with the cooler volatile gases able to form farther out. Now again, as I mentioned last time, in other solar systems, i.e. extrasolar planets, these gaseous worlds often orbit very close to their stars. So while it's likely that they formed farther out where those gases could condense, they migrated in. For whatever reason, this migration did not take place in our solar system, and those gaseous worlds remained in the outer parts of our solar system. Planetesimals accreted more and more matter through collisions. And incidentally, we see this process taking place in a system called Beta Pictoris. Beta Pictoris is a star surrounded still by gas and dust from which planets are currently being formed. High-resolution images of Beta Pictoris imply that there are gaps in the cloud, similar to the ones you see pictured in part C of this diagram. This implies the existence of planets that are forming in and around that star. Once the protoplanets form, differentiation occurs as the heavier, more dense materials sink to the center through gravity, similarly to how heavier things sink in water. What you end up with is the heaviest, most dense stuff, such as iron, in the center core region, and then rock, which is less dense, farther out. The atmospheres of planets, formed by probably some combination of both outgassing from volcanic activity and also collisions from comets, which vaporized gases and released them into the atmosphere. However, as we mentioned before, holding on to an atmosphere can be a problem, especially for smaller planets that have low gravity. They're not able to hold on to thick blankets of atmosphere, and these escape into space, such is the case of Mars. But before we start talking about Mars and other planets, let's start with the closest planet to the Sun, Mercury. Mercury can be thought of as a planet of extremes. The side which faces the Sun has a surface temperature in excess of 700 degrees Kelvin, whereas on the night side of Mercury, simultaneously, the temperatures there drop as low as 70 K. Now, for reference, room temperature is around 300 K. And so this is very, very cold, actually. Absolute zero is 0 degrees Kelvin. And nothing can be colder than absolute zero. So why is it frying on one side and freezing on the other? Well, this is due to the fact that, partly due to the fact that it has no appreciable atmosphere. If it had an atmosphere, then the atmosphere would act to regulate the temperature between the night side and the day side. It's likely that whatever atmosphere Mercury may have had burned off long ago. Mercury also has a very eccentric orbit compared to the other planets. To look at it, Mercury looks very much like the Moon, although it is a little bit larger. Has many craters that overlap, similar to the Moon, and even with the rays that extend from some of the craters like the Moon. The rims of the crater are lower because Mercury has more gravity due to the fact that it is more massive. And even though some craters overlap, fewer of them do. There are some other features on Mercury's surface, such as scarps, which are kilometer-tall cliffs. Think of them as wrinkles in an apple's skin as it dries. They are due to the shrinking of the planet as it cooled. As you know, cooler things shrink, warmer things expand. There's also a feature known as the Caloris Basin on Mercury. It is a huge 800-kilometer wide crater. The crater is so large, in fact, that the shock waves traveled through the entire planet and actually shook up the terrain on the opposite side. Mercury is very dense. This implies that it has a very large core made of iron, and that its mantle, composed of silicate, is smaller than, say, the mantle of Earth. As the slide says here, this core may cause the weak magnetic field that Mercury has. To have a magnetic field, you need both some kind of metal and also some kind of rotation. While Mercury has much more metal in its core than does Earth, it rotates extremely slowly. And we'll get back to that in a moment. But first, let's ask ourselves why it is that Mercury is so dense. Why does it have this huge iron core? Well, one explanation might be that, like Earth, Mercury suffered cataclysmic collision early in its history. And this collision may have resulted in ejecting and removing a lot of the rocky material, leaving behind mostly an iron core surrounded by smaller amounts of rock. Such a collision would have been even more cataclysmic than the collision which is thought to have created the moon on Earth. But getting back to this idea of Mercury rotating on its axis slowly, it is what we call tidally locked to the sun, similar to how the moon is tidally locked to the Earth. In other words, its year is almost, or its day is almost as long as its year. Once it travels one time around the sun, it is only rotated on its axis 1.5 times. So this slow rotation may explain why the magnetic field on Mercury is so weak. And also having one face towards the sun for an extended period of time also helps us understand why that side of the planet is so fried while the other side is frigid.